Okay, so in the last lecture we discussed the concept of Thevenin models and how to model a circuit with its Thevenin equivalent. Now we're going to move on to the second dual of the Thevenin model, which is called the Norton model. So with the Thevenin model, if you recall, we had a voltage source in series with a resistor, or generally speaking an impedance. We still don't know what an impedance is, but the general case, that's how we show it. So voltage source with a resistor in series, and in the case of a Norton model, it's a current source with a resistor, or impedance for that matter, in parallel to the current source. Now, so our approach was that we assume that this hypothesis is true, and then we go by the very intuitive assumption that if these two are equivalent to each other, whatever happens to this circuit has to be true about that circuit, assuming that the situation for both is the same. Now, with the case with the voltage source in series with a resistor, or Thevenin model, we said we first leave it open and look at what would be the voltage across terminal, because that would directly give us the Thevenin voltage. In the case of a Norton model, what we can do is exactly the dual of that. In other words, we're going to actually short it out. So if we put a short circuit here and look at the current that is passing through this circuit, if you analyze this circuit, it's very simple to see that the current of I short circuit is actually equal to IN. So let's make sure that we understand that. Again, if you want to prove it, just follow the three-step process. But it's really simple to see. If this is a short circuit, this voltage is equal to that voltage. Therefore, the current that is passing through this resistor is actually zero, because the current that is passing through a resistor is voltage on one side minus the voltage on the other side divided by the resistance. And we just said the voltage across these are the same because it's a short circuit. So the current passing through that resistor is zero. And if you write a KCL for that node, current in is IN, this is zero, and current out is I short circuit. So all the current is going to actually bypass the resistor and pass through the short circuit. A very intuitive result of shorting out the component. When you say we are shorting out a component, what it means is really that the current that would otherwise pass through that component would actually now go through that short. Okay, so if that's the case for this hypothetical model of that circuit, then the same thing has to be true with this circuit. In other words, if I connect these two terminals to each other and look at I short circuit, this current has to be equal to I Norton. So to calculate I Norton, that's exactly what I'm going to do. I'm going to look at, short these two terminals, assuming that this whole thing is in a box, and then calculate the value for that short circuit current, and that would be the I Norton that I'm looking for. Okay, so in order to accomplish that, we go back to circuit analysis. That's labeling the nodes. So that's one node, one node, one node. And now in this case, this node is actually the same node. So this node is actually the same node because that's connected. So current, start labeling the currents actually. So that's 25 volts again. So that's 25. Equation for that component means that that's 25. I'm going to call that V1. This voltage here, if I say this is ground, this is 0, and that's also 0. Now, that's 3. I'm going to call this I1. That would be also I1, KCL for that node. This I'm going to call I2. This is 3 amp. And that, the KCL for this node tells you that that current that is going in and this current are the same, so that's your I short circuit. So it's the same I short circuit that passes through the 4 amp, right? And the voltage of this whole thing is now 0 because they're connected to each other. So we're done labeling. We're going to start writing the KCL. There's only really one KCL to write the equation for, KCL. For that one, again, 3 amp is going in, I1 is going in, and I short circuit and I2 are leaving that node. So I short circuit plus I2 is equal to 3 plus I1, and that's the only KCL that we have to write. Then we move on to the equations for components. Again, we have 1, 2, 3, 4, 5 components. Those two are already taken care of. So these are the 3 components where I write the equations for them. So I1 is equal to 25 minus V1 divided by 5. I2 is equal to V1 minus 0 divided by 20. And finally, I short circuit. That's V1 minus the voltage here, and it's a short circuit, so that's 0. So this is 0, so that's 0. So that would be V1 minus 0 divided by 4 ohm. Once we do that, then we start actually taking these 3 equations and putting them in the KCL. So V1 divided by 4 plus V1 divided by 20 has to be equal to 3 plus 25 minus V1 divided by 5. Multiply both sides by 20. That means 5V1 plus V1 is equal to 3 plus 100 minus 4V1. Moving all the V1s. Sorry, this is not 3. That's 3 times 20. That's 60. So moving all the V1s to one side, that's 6 plus 4. That's 10V1 is equal to 160. So V1 is 16 volts this time. Okay, now we take the value of V1 and calculate the current. I short circuit is equal to 16 divided by 4, which is 4 amp. And that is your Norton current. So now you know that this value is 4 amp. Great. So we have I Norton. So it's time to now look at a way to calculate the Norton resistance. So for that, again, if I go back, now let's clear that. If I go here for this hypothetical model and turn off the source that exists here, and turning off the current source means that the current has to be 0, meaning that it has to be opened up. So if that's opened up, looking back into these 2 terminals, the resistance that I see is R Norton, and therefore the same thing has to be true for this circuit. In other words, if I short this out and open this up, looking back into this circuit, I have to calculate the same value, which means whatever I see here, that's my R Norton. But if you recall, we've already done that for our Thevenin modeling. So I'm just going to quickly repeat that. This was the model that we ended up getting. So that's my 4 ohm, that's the 5 ohm, that's the 20 ohm. Looking to this, we said our equivalent is equal to 4 plus 20 in parallel with 5, which ended up being 8 ohms. And now that's also my Norton equivalent resistance. And that concludes our calculations or modeling of the circuit with the Norton equivalent. So again, to recap, we could choose either a voltage source in series with a resistor, which was called a Thevenin model, as the equivalent for this circuit, or a current source in parallel with a resistor, which is called the Norton model. We already took care of the Thevenin modeling and how to do that. With the Norton modeling, you take the 2 terminals and connect them to each other, short circuit the 2, and once you do that, the current that is passing through that short circuit has to be equal to IN. In other words, to calculate IN, you just short circuit that, and that current is the value of IN in this circuit, because these 2 are equivalent to each other. And then you turn off all the independent sources, meaning the voltage source is going to be a short circuit, the current source is going to be an open, And once you do that, looking back into the circuit, you calculate the equivalent resistance, and that would be your Norton resistance. That concludes Norton model. Now, with this, the next lecture, we're going to actually kind of compare the Norton and Untitled model side by side and get more insight into how we may be able to go from one to the other without repeating the calculation. In other words, once you have calculated one of these two models, there's a certain shortcut that you can take, which I'll explain to you and is intuitive, and you can quickly go from one model to the other without really going through much of a calculation. Thank you for your attention, and see you in the next lecture.